Take a moment right now. Reach for your glass of water, or simply think about the last sip you took. That water, that simple, clear liquid that passes your lips without ceremony, without fanfare, has traveled through time in ways that would make even the most elaborate science fiction seem mundane by comparison. The water molecules you drink today are older than the sun itself. They're older than Earth, older than the moon, older than the entire solar system. They existed before there were planets, before there was a star to warm them, before there was anything we would recognize as our cosmic neighborhood. This isn't a poetic metaphor. This isn't scientific hyperbole. This is the extraordinary reality uncovered by decades of research, countless observations, and samples brought back from the very edge of space. When you hold that glass in your hand, you're holding something that predates the formation of our home star by potentially hundreds of millions of years, perhaps even longer. You're holding molecules that formed in the frigid darkness between stars, in clouds so vast they dwarf our entire solar system, in conditions so alien and so cold that they challenge our everyday understanding of chemistry itself. Today, we're going to trace that journey. We're going to follow water from its origins in the aftermath of the Big Bang, through the stellar nurseries where our sun was born, onto the asteroids and comets that delivered it to our planet, and finally into the glass you hold in your hand. It's a story that spans nearly 14 billion years, crosses incomprehensible distances, and touches on some of the most fundamental questions humans have ever asked about our place in the universe. To understand how water came to be older than our sun, we need to go back to the very beginning. Not the beginning of Earth, not the beginning of our solar system, but the beginning of everything. The Big Bang itself, approximately 13.8 billion years ago. In those first moments, the universe was unimaginably hot and dense. Matter as we know it didn't exist yet. There were no atoms, no molecules, just a seething soup of fundamental particles. But as the universe expanded and cooled, something remarkable happened. Within the first few minutes, specifically between about 10 seconds and 20 minutes after the Big Bang, conditions became just right for the first atomic nuclei to form. This process, called Big Bang nucleosynthesis, was brief but crucial. As the temperature dropped to around 1 billion degrees, Kelvin neutrons and protons began to combine in specific ways. They formed deuterium, an isotope of hydrogen with an extra neutron in its nucleus. Then they formed helium and trace amounts of lithium. But hydrogen, simple ordinary hydrogen with its single proton and single electron, emerged as the overwhelming winner. About 75% of all matter became hydrogen. Another 25% became helium. Everything else was just traces. Now here's where our water story truly begins. That hydrogen from the Big Bang, it's still around. In fact, most of the hydrogen in the universe today is primordial. It's the same hydrogen that formed in those first minutes. And water, as we all know, is made primarily of hydrogen. 2 hydrogen atoms are bonded to 1 oxygen atom. So in a very real sense, half of every water molecule is as old as the universe itself. But what about the oxygen? That's where things get interesting. Oxygen didn't exist yet. The Big Bang didn't produce oxygen in any significant quantity. For oxygen to exist, the universe needed stars. Fast forward about 400 million years, the universe had cooled considerably. Clouds of hydrogen and helium began to collapse under their own gravity, growing denser and hotter in their cores. When the temperature and pressure at these cores reached critical thresholds, nuclear fusion ignited. The first stars blazed into existence, lighting up a universe that had been dark for hundreds of millions of years. These early stars were massive, brilliant, and short-lived by cosmic standards. In their cores, they did what stars do best. They cooked lighter elements into heavier ones. Hydrogen fused into helium, helium fused into carbon, carbon fused with oxygen. The cosmic oven was baking the ingredients for water, though water itself still couldn't form in any appreciable quantity. Stars are too hot. Their interiors are too violent. Water molecules would be instantly destroyed in those conditions. But when these massive stars died, and they died spectacularly in supernova explosions that outshone entire galaxies, they scattered their hard-won elements into space. Oxygen, carbon, nitrogen, silicon, iron, and dozens of other elements spread out into the interstellar medium, mixing with the primordial hydrogen that had been floating there since the Big Bang. And it's in that interstellar medium, in the cold darkness between the stars, that water finally had its chance to form. The space between stars is not empty. We call it space, but that's a misnomer born of our human-scale perspective. The interstellar medium contains gas, mostly hydrogen, and tiny particles of dust, grains smaller than bacteria, composed of silicates, carbon, and other elements forged in previous generations of stars. In the densest regions of the interstellar medium, these materials collect into structures called molecular clouds. And cloud is itself almost too gentle a word for what these structures are. Molecular clouds can be hundreds of light years across, containing enough material to make thousands, sometimes millions, of stars. They're monuments to gravity and chemistry, operating on scales that dwarf human comprehension. Inside these clouds, the conditions are extreme by our standards, though in a completely different way than stellar interiors. Temperatures hover around 10 Kelvin, that's negative 263 degrees Celsius, just 10 degrees above absolute zero. Densities are remarkably low by terrestrial standards, perhaps 100 to a million particles per cubic centimeter. On Earth, air at sea level contains about 10 to the 19, that's 10 million trillion, molecules per cubic centimeter. So even the dense molecular clouds are vacuum by our everyday standards. But at these cold temperatures, magic happens. Oxygen atoms and hydrogen atoms in the gas phase collide with the surface of dust grains, and they stick. The frigid temperatures rob them of the energy they'd need to bounce away. Over time, thin mantles of ice build up on these dust grains, coating them in layers of frozen molecules. Here, in the darkness and cold, water forms. A hydrogen atom lands on a grain, then another, then an oxygen atom. Given enough time and enough collisions, they find each other on the grain's surface. They react, they bond. Water is born. But not just water. These grain surfaces become tiny laboratories for chemistry that simply cannot happen in the gas phase. Carbon monoxide freezes onto the grains, ammonia forms, methanol, carbon dioxide. The mantles become rich mixtures of ices, and water is the dominant component, typically making up 60 to 70% of the ice by mass. This is where the age becomes crucial. These molecular clouds exist for tens of millions, sometimes hundreds of millions of years before anything disturbs them. The water ice coating the grains inside them is forming, reforming, accumulating over those vast spans of time. And remember, this is all happening in the interstellar medium before any particular star system forms, before our sun existed, before our solar system began to coalesce. The water forming in these clouds carries a unique signature, a kind of chemical fingerprint that we can still detect today, billions of years later. That signature lies in the ratio of deuterium to regular hydrogen. Deuterium is heavy hydrogen. Where regular hydrogen has one proton in its nucleus, deuterium has one proton and one neutron. That extra neutron doesn't change the chemistry much. Deuterium bonds with oxygen just like regular hydrogen does, forming heavy water or semi-heavy water depending on how many deuterium atoms are present. But that extra neutron does make deuterium behave slightly differently in chemical reactions. In the frigid conditions of molecular clouds, deuterium preferentially gets incorporated into molecules over regular hydrogen. The reasons are quantum mechanical, having to do with the different vibrational energies of bonds containing deuterium versus regular hydrogen. But the upshot is straightforward. Water formed in extremely cold conditions ends up enriched in deuterium compared to water formed at higher temperatures. This gives us a tool, a tracer, a way to follow water's journey through space and time. By measuring the ratio of deuterium to hydrogen, the D to H ratio as scientists call it, in water found in different locations, we can determine where and when that water formed. The water on Earth in our oceans has a D to H ratio of about 1.56 times 10 to the negative 4. That means for every 6,420 hydrogen atoms in ocean water, there's one deuterium atom. It sounds like a tiny fraction, and it is, but it's measurable, and it's distinctive. When scientists measure the D to H ratio in different objects in the solar system, they find a range of values. The Sun and the gas giant planets have low D to H ratios, close to what we'd expect from the original solar nebula, about 2.1 times 10 to the negative 5. This makes sense. The Sun formed from the collapse of gas, and that gas had a composition relatively unchanged from the Big Bang. But comets. Some comets have D to H ratios 2 or 3 times higher than Earth's oceans. Carbonaceous asteroids tend to have ratios that match Earth's water quite closely. And water observed in distant molecular clouds, the stellar nurseries where new stars are being born today, has even higher D to H ratios, sometimes 10 times or more above the solar value. This deuterium enrichment in cold molecular clouds is the signature of ancient water. When water forms at temperatures of 10 or 20 Kelvin in the darkness between stars, it picks up extra deuterium. That enrichment becomes frozen into the ice, a timestamp of sorts, recording the conditions under which that water came into being. And here's the crucial point. If water forms in a hot environment, like a newly forming stellar system, the deuterium enrichment gets erased. Chemical reactions at higher temperatures favor the lighter isotope, hydrogen, and the D to H ratio drops toward the solar value. But if water is inherited from a cold molecular cloud, if it survives the violent process of star formation without being completely broken apart and reformed, it retains its high D to H ratio, its signature of age and cold. For decades, scientists have been measuring these ratios in samples returned from comets, in meteorites that have fallen to Earth, in spectra taken of distant objects. They've been building up a picture, piece by piece, of where the water in our solar system came from. And increasingly, the evidence points to the same conclusion. Much of the water didn't form in our solar system at all. It was inherited from the molecular cloud that gave birth to our Sun. About 4.6 billion years ago, something disturbed a particular molecular cloud on the outskirts of our galaxy. Perhaps it was the shockwave from a nearby supernova. Perhaps it was the gravitational influence of a passing star or the compression of a spiral density wave passing through the galaxy. Whatever the trigger, a region of this cloud began to collapse. Gravity is patient but inexorable. The collapsing region grew denser. As it contracted, it began to spin faster, conserving angular momentum like an ice skater pulling in their arms. Material fell toward the center, and as it did, it flattened into a disk, the protoplanetary disk that would eventually give birth to our Sun and all the planets. At the center of this disk, density and temperature soared. After about 50 million years of contraction, the core became hot enough and dense enough for hydrogen fusion to ignite. Our Sun was born. But what happened to the water during this violent process? Did it survive, or was it destroyed and reformed? This question is at the heart of understanding Earth's water. If the water in our solar system formed fresh during the Sun's birth, then it would have a D to H ratio characteristic of those conditions, probably similar to the solar ratio, with relatively little deuterium enrichment. But if some or all of the water was inherited from the parent molecular cloud, it would retain a higher D to H ratio, a memory of its cold, ancient origin. For many years, this was an open question. The problem was that we couldn't directly observe the process. We couldn't watch the formation of a solar system like ours and track what happened to the water. The best we could do was study our own solar system's water and make educated guesses about its history, or look at other young stellar systems and try to infer what might have happened in ours. Then, in 2023, a crucial observation changed everything. Using the Atacama Large Millimeter-Submillimeter Array, ALMA, a collection of 66 radio telescopes in the Chilean desert, astronomers observed a young star system called V8883 Orionis, located about 1,300 light-years from Earth in the constellation Orion. V8883 Orionis is a protostar, still in the process of gathering material from its surrounding disk. Normally, the water in such disks is frozen as ice, locked into the solid grains and invisible to our telescopes. But V883 Orionis had experienced an outburst, a sudden brightening that heated its inner disk to temperatures where water could exist as vapor. That vapor could be detected by ALMA. The researchers measured the D to H ratio in the water vapor around V883 Orionis, and they found something remarkable. It matched the ratios seen in comets in our own solar system. More than that, it matched the ratios seen in the molecular clouds where stars form today. This was the missing link. Here was direct evidence that water could survive the violent process of star formation, that it could be inherited from the parent cloud rather than being destroyed and reformed. The composition of the water in V883 Orionis's disk is remarkably similar to water in our solar system's comets, and both are remarkably similar to water in the molecular clouds where they originally formed. The chain was complete. Astronomers could now trace water from molecular clouds to protostars to planet-forming disks to comets. And at each step, the deuterium signature remained largely intact. The water was ancient, it predated the sun, it had formed in the darkness and cold, and it had survived. In October 2025, the V883 Orionis team made another groundbreaking announcement. They had detected doubly deuterated water, D2O, where both hydrogen atoms are replaced with deuterium. This is even rarer than semi-heavy water, and its presence provides even stronger evidence that the water is pristine, inherited directly from the ancient molecular cloud without being reprocessed in the disk. The ratio of heavy water to regular water in V883 Orionis is the same as in molecular clouds before they form any stars. The verdict was in. Our water didn't form when the sun did. It's older. Potentially hundreds of millions of years older. It formed in the cold interstellar medium, coated tiny dust grains with ice, and somehow survived the chaos of stellar birth to become part of our world. Understanding that water predates the sun is one thing. Understanding how it got to Earth is another. Because there's a problem, and it's a significant one. Earth formed too close to the sun. To truly appreciate this dilemma, we need to journey back approximately 4.5 billion years to a time when our solar system was nothing more than a vast spinning disk of gas and dust surrounding a newly igniting star. This disk, known as the protoplanetary disk or solar nebula, contained all the raw materials that would eventually become the planets, moons, asteroids, and comets we observe today. Within this disk, temperatures varied dramatically depending on distance from the young sun. Close to the star, where solar radiation was intense, temperatures soared to thousands of degrees. Further out in the cold darkness beyond the reach of the sun's warming influence, temperatures plunged to levels that would make the coldest Antarctic winter seem tropical by comparison. In the early solar system, the young sun's heat created a pronounced temperature gradient in this protoplanetary disk. Picture the disk as a vast, flattened cloud of material, with the proto-sun blazing at its center like a cosmic furnace. The temperature within this disk followed a predictable pattern, decreasing steadily with distance from the central star. Close to the sun, temperatures were extraordinarily high, reaching well above 1,000 degrees Celsius in the innermost regions. These scorching temperatures meant that only the most refractory materials, those with the highest melting points, could exist as solids. Iron, nickel, silicates, and various rock-forming minerals could condense and remain solid, but anything more volatile simply could not survive in solid form. Further out in the disk, past a critical boundary that scientists call the frost line, or sometimes the snow line or ice line, temperatures finally dropped low enough for water ice to remain stable. This frost line represents one of the most important boundaries in planetary science. It marks the transition between the inner solar system, where water could only exist as vapor, and the outer solar system, where water could freeze into solid ice and be incorporated into growing planetary bodies. The exact location of this frost line has been the subject of considerable scientific investigation. According to models developed by Chushiro Hayashi and collaborators at Kyoto University, who established the foundational framework for understanding protoplanetary disk structure. The water frost line was probably located somewhere around 2.7 astronomical units from the Sun, roughly in the middle of what is today the asteroid belt. More recent models by researchers like Podolak and Zucker have suggested the line may have been slightly further out, perhaps between 3 and 3.2 astronomical units, depending on the specific conditions assumed for the early solar nebula. The temperature at this critical boundary, where water transitions between vapor and solid ice, is approximately 150 to 170 Kelvin, which translates to roughly -100 to -120 degrees Celsius. This temperature range represents the point at which water vapor in the low-pressure environment of the protoplanetary disk will deposit directly onto dust grains as ice without passing through a liquid phase. This process of direct vapor to solid transition is known as deposition, and it played a crucial role in determining where water could be incorporated into forming planetary bodies. But here's the critical detail that makes Earth's abundance of water so puzzling. Earth formed at approximately 1 astronomical unit from the Sun. 1 astronomical unit is the average distance between Earth and the Sun, roughly 150 million kilometers or 93 million miles. This places Earth well inside the frost line, deep within the zone where water could not have existed as ice during the planet's formation. At Earth's location in the early protoplanetary disk, water simply couldn't have existed in solid form. Any water molecules present in the region where Earth was assembling would have been in the form of vapor, drifting through the hot inner disk as individual molecules rather than clinging to dust grains as ice. And vapor, unlike ice, is extremely difficult to incorporate into a growing planet. The young sun's intense radiation and powerful stellar winds would have driven water vapor away, pushing it outward into the colder regions of the disk or stripping it from the system entirely. This raises a fundamental question that has puzzled planetary scientists for decades. If Earth formed in a region of the solar system where water ice couldn't exist, how did our planet end up with so much water? The oceans covering 70% of Earth's surface represent only a fraction of our planet's total water inventory. There's water locked in minerals deep within the mantle, water frozen at the poles, and water cycling through the atmosphere as vapor and clouds. Some estimates suggest that Earth's mantle alone might contain several times more water than all the surface oceans combined. Where did all this water come from? The answer, increasingly clear from multiple converging lines of evidence, is that water was delivered to Earth after its initial formation, carried by objects that originally formed beyond the frost line and subsequently migrated inward to collide with our planet. This process of late delivery, occurring after Earth had already substantially assembled, is the key to understanding why our planet is so remarkably wet despite having formed in the driest part of the solar system. But the frost line story is more nuanced and dynamic than a simple fixed boundary might suggest. Recent research has revealed that the frost line's location shifted over time as the protoplanetary disk evolved. During the earliest phases of disk evolution, when accretion onto the young sun was most vigorous and the disk was actively heated by gravitational energy release, the frost line may have been pushed outward to distances as far as 17 astronomical units, nearly to the orbit of present-day Uranus. As the disk cooled and accretion slowed, the frost line gradually migrated inward, sweeping through the asteroid belt region and potentially even approaching the orbit of Mars. This dynamic frost line behavior has important implications for understanding where and when water-rich bodies could form. Studies by researchers at Astrobites and other institutions have shown that regions of low turbulence in the protoplanetary disk, known as dead zones, may have kept the frost line farther from the sun for extended periods. This would have provided more time for the inner solar system, including the region where Earth formed, to remain relatively dry during the planet-building process. The frost line also marks a critical boundary for planet formation itself. Beyond this line, the abundance of solid material increases dramatically. Ice represents a substantial fraction of the available mass in the outer disk, and this sudden increase in solid surface density changes everything about how planets can form. Planetesimals, the building blocks of planets, can grow much more massive beyond the frost line because there's simply more solid material available to build with. This is why the giant planets, Jupiter, Saturn, Uranus, and Neptune, all formed in the outer solar system. Their massive cores grew rapidly in the ice-rich regions beyond the frost line, accumulating enough mass to gravitationally capture enormous atmospheres of hydrogen and helium gas before the disk dissipated. Recent work has also illuminated the crucial role of a process called streaming instability in forming planetesimals at and beyond the frost line. In this process, solid particles in the disk, ranging from dust to pebbles, can spontaneously clump together under the right conditions. When the local density of solid particles exceeds the density of the surrounding gas, these particles begin to gravitationally attract each other, rapidly collapsing to form kilometer-sized planetesimals. Research published in Astronomy and Astrophysics has demonstrated that the conditions for streaming instability are particularly favorable just outside the frost line, where ice recondensing onto pebbles can enhance the local solid-to-gas ratio. Water vapor diffusing outward across the frost line deposits as ice on pebbles already present, effectively making them larger and more massive and creating ideal conditions for planetesimal formation. This is why some scientists believe that planetesimal formation may have preferentially begun at the frost line, with the first asteroids and comet nuclei forming in a ring-like zone just beyond where water could freeze. These early planetesimals, rich in water ice from their formation beyond the frost line, would later become the reservoirs from which Earth's water was drawn. Two main candidates have been proposed as the delivery vehicles for Earth's water: comets and asteroids, specifically carbonaceous asteroids. Comets are icy bodies that form in the frigid outer reaches of the solar system beyond Neptune, in regions called the Kuiper Belt and the Oort cloud. These distant reservoirs are so cold that temperatures hover near absolute zero, allowing not just water ice, but also more volatile ices like carbon monoxide, carbon dioxide, and nitrogen to remain frozen. Comets are essentially dirty snowballs, or perhaps more accurately, icy dirt balls, with water ice making up a substantial fraction of their mass, along with rocky and carbonaceous materials. Asteroids, meanwhile, formed mostly in the asteroid belt between Mars and Jupiter, a region that straddles the frost line. The asteroid belt is not uniform in composition. The inner belt, closer to Mars, contains primarily rocky asteroids composed of silicates and metals. But the outer belt, approaching Jupiter's orbit, contains a population of darker, more primitive asteroids that are rich in carbon and, crucially, contain significant amounts of water. These carbonaceous asteroids, particularly those belonging to the C-type classification, contain water not as free ice, but bound up in minerals, incorporated into the crystal structures of hydrated silicates, trapped as hydroxyl groups in various compounds, and present in clay minerals that formed through ancient reactions between rock and liquid water. For decades, comets were considered the most likely source of Earth's water. The reasoning seemed intuitive. Comets are manifestly rich in water. You can see it vaporizing off their surfaces as they approach the sun, forming the spectacular tails that give comets their name. Countless comets have struck Earth over its 4.5 billion year history. The inner solar system was especially crowded with cometary material during the first few 100 million years, a time of intense bombardment. Surely, the thinking went, these icy visitors delivered our oceans. But then scientists developed techniques to measure the isotopic composition of cometary water, and the story became considerably more complicated. The deuterium to hydrogen ratio, that crucial isotopic fingerprint we discussed earlier, became the key to testing the cometary hypothesis. When astronomers began measuring the D to H ratios in comets, they found something unexpected. Many comets, particularly those from the distant Oort cloud, had D to H ratios that were about twice as high as Earth's ocean water. This seemed to rule out Oort cloud comets as a primary source. Their water was simply too heavy. too enriched in deuterium to match what we find in Earth's oceans. Then, a few comets from the Jupiter family were measured. These are comets that orbit in the inner solar system, with orbital periods typically less than 20 years, and whose paths are strongly influenced by Jupiter's gravity. They are thought to originate from the Kuiper belt, the disk of icy objects beyond Neptune, rather than the more distant spherical Oort cloud. One comet in particular, Hartley 2, was measured during a flyby by NASA's EPOXY mission in 2010, and its D to H ratio proved nearly identical to Earth's ocean water. This result revived the comet hypothesis. Maybe Jupiter family comets, originating from the Kuiper belt rather than the Oort cloud, had delivered our water after all. The debate was far from settled. Different comets showed different D to H ratios, and the sample size was small. Scientists needed more data, more measurements from more comets to draw definitive conclusions. And then, in 2014, a European Space Agency mission arrived at a Jupiter family comet and began the most comprehensive study of any comet in history. Then came the Rosetta mission. In August 2014, the European Space Agency's Rosetta spacecraft arrived at Comet 67P Churyumov-Gerasimenko, a Jupiter family comet with a distinctive shape that would soon earn it the nickname the Rubber Duck Comet. This particular comet, designated 67P for short, stretches approximately 4 kilometers across at its widest point, with two distinct lobes connected by a narrow neck that gives it that peculiar duck-like silhouette. For the next 2 years, Rosetta would orbit this cosmic wanderer, observing it in unprecedented detail as it approached the Sun, heated up, and became increasingly active, spewing jets of gas and dust into space. The Rosetta mission represented one of the most ambitious and complex space exploration endeavors ever attempted. The spacecraft had launched a decade earlier, in March 2004, and spent 10 years making multiple gravity assist flybys of Earth and Mars, plus 2 asteroid encounters, to build up enough velocity to catch 67P on its journey around the Sun. The orbital mechanics required to rendezvous with a comet are extraordinarily challenging. Unlike a planet, which follows a predictable path around the Sun, a comet is a small, dark object moving at high speed on an elongated elliptical orbit. Matching that orbit while carrying enough fuel to maneuver and operate for years required every trick in the space navigation playbook. But the technical challenges were worth the effort, because comets like 67P represent pristine samples of the early solar system. They formed in the cold outer reaches of the solar nebula beyond the frost line, accumulating water ice and other volatile ices, along with rocky and carbonaceous dust. Since their formation 4.5 billion years ago, they have been stored in the deep freeze of the outer solar system, preserved in a state that has changed relatively little. When a comet approaches the Sun and becomes active, the gases it releases are essentially the same gases that were frozen into it during its formation. By analyzing those gases, scientists can peer back in time to understand the conditions and composition of the early solar system. In November 2014, just 3 months after arrival, Rosetta deployed a lander called Philae, which became the first spacecraft ever to land on a comet's surface. The landing was anything but smooth. Philae's harpoons failed to fire, and the lander bounced across the comet's surface in the weak gravity, eventually coming to rest in a shadowy crevice where its solar panels couldn't receive enough light to keep it powered. Despite these challenges, Philae managed to return valuable data about the comet's surface composition before falling silent. But the real workhorse of the mission was Rosetta itself, which continued to orbit and study 67P until September 2016, when mission controllers deliberately crashed it into the comet's surface, ending the mission in a final burst of close-up observations. Among Rosetta's many scientific instruments was Rosina, an acronym for the Rosetta Orbiter Spectrometer for ion and neutral analysis. This sophisticated mass spectrometer suite could analyze the composition of gases surrounding the comet, identifying specific molecules and measuring the relative abundances of different isotopes. One of Rosina's most important measurements was the deuterium to hydrogen ratio in the water vapor streaming off the comet as it warmed during its approach to perihelion, the closest point in its orbit to the Sun. The initial results, announced in December 2014 and published in the journal Science, were startling and seemed to deal a fatal blow to the idea that comets like 67P had delivered Earth's water. The D to H ratio measured by Rosina was approximately 5.3 times 10 to the negative fourth, which works out to more than 3 times higher than the ratio in Earth's ocean water. This was, at the time, the highest D to H ratio ever measured in any solar system object. If 67P was representative of Jupiter family comets, then these comets were far too deuterium-rich to have been the primary source of Earth's water. This finding casts serious doubt on the comet hypothesis. The scientific community had expected Jupiter family comets to have D to H ratios similar to Earth's, based on the earlier Hartley 2 measurement and theoretical models of how these comets should have formed. The 67P result seemed to suggest that the earlier Hartley 2 measurement might have been anomalous, or that the diversity among Jupiter family comets was far greater than expected. Either way, it appeared that comets were unlikely to have delivered the bulk of Earth's water. Attention shifted decisively to asteroids, particularly the carbonaceous asteroids found in the outer regions of the main belt. These asteroids, darker and more primitive than their rocky inner belt counterparts, contain minerals that formed in the presence of liquid water. Analysis of meteorites derived from these asteroids, known as carbonaceous chondrites, consistently showed D to H ratios that matched Earth's ocean water remarkably well. The asteroid hypothesis gained strength as researchers accumulated more data showing that carbonaceous chondrite meteorites could account for Earth's water isotopically, while comets apparently could not. But science is never quite finished, and good scientists are always revisiting previous results with new methods and fresh perspectives. There was something odd about the Rosetta measurements that nagged at researchers familiar with the data. The Rosina measurements varied depending on where the spacecraft was relative to the comet, depending on the comet's activity level, and especially depending on how dusty the environment was around the spacecraft. The published D to H ratio was an average, but the individual measurements showed significant scatter. Sometimes the ratio was higher, sometimes lower, and the variation seemed to correlate with environmental conditions in ways that weren't fully understood. In November 2024, nearly a decade after the initial surprising results, a team of researchers led by Kathleen Mant of NASA's Goddard Space Flight Center published a groundbreaking new analysis of the complete Rosetta dataset. Mant and her colleagues, which included researchers from Johns Hopkins Applied Physics Laboratory, the University of Bern in Switzerland, Auburn University, and several other institutions, brought fresh eyes and new analytical techniques to the massive trove of Rosina data. They used advanced statistical methods, including techniques originally developed for analyzing exoplanet observations, to carefully separate the contributions of different processes to the measured deuterium ratios. Their analysis encompassed more than 4,000 individual water isotope measurements collected over the full duration of the Rosetta mission. Rather than simply averaging all the data together, they systematically examined how the D to H ratio varied with distance from the comet nucleus, with the comet's activity level, and with the amount of dust in the local environment. They identified signals coming specifically from deuterium-containing water molecules, carefully filtering out potential contamination and instrumental artifacts. What they found was remarkable and has fundamentally changed our understanding of cometary contributions to Earth's water. The high deuterium measurements that had dominated the earlier analysis were coming primarily from water attached to dust grains, not from the bulk ice of the comet nucleus. Here's what happens. As the comet's surface is heated by approaching sunlight, water ice sublimates, turning directly from solid to gas. This process exposes dust grains that had been embedded in the ice. These newly exposed dust grains have surfaces that can absorb water molecules, and crucially, deuterium-containing water molecules, HDO, preferentially stick to these surfaces compared to ordinary H2O. The heavier water molecule has slightly different quantum mechanical properties that make it adsorb more readily. This creates a situation where dust grains become coated with deuterium-enriched water ice, even though the bulk ice in the comet nucleus has a different, lower D to H ratio. When Rosetta flew close to the nucleus through dusty regions of the coma, Rosina was measuring a mixture of water from the nucleus ice and deuterium-enriched water from dust grain surfaces. The closer to the nucleus, the dustier the environment, and the more the measurements were skewed toward artificially high D to H values. The team realized they needed to identify regions where the gas from the nucleus had thoroughly mixed, and the dust had largely sublimated away, leaving primarily the water that represents the bulk composition of the comet. They found that at distances of approximately 120 kilometers from the nucleus, the gas was well mixed, and the dust was essentially dried out, its volatile coatings having sublimated. Using only measurements from these cleaner environments, they calculated what the nucleus water alone should be. The result was a D to H ratio approximately 1.5 times that of Earth's ocean water, dramatically lower than the original measurement of 3 times Earth's value. This revised ratio brings Comet 67P into line with other Jupiter family comets like Hartley 2 and 45P, Honda-Merkos-Pajdusakova, all of which show D to H ratios relatively close to terrestrial values. This was a bombshell that reverberated through the planetary science community. Comet 67P's water is much more Earth-like than previously believed, and since 67P is a Jupiter family comet representative of a huge population of similar objects originating from the Kuiper belt, it means that Jupiter family comets could indeed have been significant contributors to Earth's oceans after all. The MANT team's analysis also shed light on how the earlier measurements had been misleading. The original 2014 analysis was conducted when Rosetta was orbiting relatively close to the nucleus during a period of high cometary activity, conditions that maximized the dust contribution and skewed the measurements toward artificially high D to H values. It wasn't that the original measurements were wrong, exactly. They accurately reflected what Rosina was detecting. But they were measuring a mixture of different water sources rather than the composition of the nucleus ice alone. The team's paper, published in Science Advances, also explored the physical and chemical processes that create deuterium-enriched layers on comet dust. They proposed a cycle in which dust grains are repeatedly exposed, coated, ejected into the coma, partially stripped of their volatile coatings, and then redeposited onto the nucleus surface in colder regions. During perihelion, when the comet is most active, fresh dust with newly enriched ice layers is released. This dust can be redeposited onto the nucleus during quieter periods, creating a layered structure where the most deuterium-enriched material is at the surface, having been processed through multiple cycles of heating and cooling. This work also has implications for understanding where 67P formed. The lower D to H ratio suggests that the comet may have formed closer to the Sun than the original high ratio implied. Water D to H ratios in the solar system generally correlate with formation distance. Objects that formed in colder regions tend to have higher ratios due to temperature-dependent isotope fractionation processes. A D to H ratio closer to Earth suggests that 67P and similar comets formed in a relatively warm region of the outer solar system, perhaps in the vicinity of the giant planets, rather than in the frigid depths of the primordial Kuiper belt. The comet versus asteroid debate wasn't over, but it had been dramatically reopened. Both sources now seemed viable as significant contributors to Earth's water. And perhaps the most likely answer, supported by the weight of accumulating evidence, was that both contributed. Asteroids delivered a substantial fraction of Earth's water during the planet's formation and the subsequent late Veneer period. Comets added additional water during the heavy bombardment phases that punctuated Earth's early history. The precise proportions remain uncertain and are the subject of ongoing research, but the revised Rosetta analysis ensures that comets remain important players in the story of how our planet became a water world. While the Rosetta mission was transforming our understanding of comets, other spacecraft were investigating the other major candidates for Earth's water delivery: asteroids. And what these missions discovered provides some of the most compelling evidence yet that carbonaceous asteroids were major contributors to our planet's water inventory. In September 2023, NASA's OSIRIS-REx spacecraft returned to Earth carrying something unprecedented: pristine samples collected directly from the surface of the asteroid Bennu. This was the first U.S. mission to collect samples from an asteroid's surface and bring them safely home, and it culminated a 7-year odyssey that had taken the spacecraft across hundreds of millions of kilometers of space. OSIRIS-REx, an acronym standing for Origins, Spectral Interpretation, Resource Identification, and Security Regolith Explorer, launched in September 2016 and arrived at Bennu in December 2018. For nearly 2 years, it mapped and characterized this small, roughly 500-meter-wide asteroid in extraordinary detail before making its dramatic sample collection maneuver in October 2020. Bennu is what astronomers call a B-type asteroid, a subcategory of the broader carbonaceous asteroid class. These objects are among the most primitive bodies in the solar system, thought to have remained largely unchanged since the earliest epochs of planet formation. They're dark, reflecting only a few % of the sunlight that hits them, and spectroscopic observations suggested that Bennu contained carbon-rich materials and water-bearing minerals. This made it an ideal target for a sample return mission aimed at understanding the raw ingredients that went into building the planets and potentially seeding them with water and organic compounds. The sample collection itself was a nerve-wracking operation. OSIRIS-REx descended slowly toward a carefully selected site named Nightingale, located in a crater in Bennu's northern hemisphere. At the moment of contact, the spacecraft extended its sampling arm, called TAGSAM, touch-and-go sample acquisition mechanism, and fired a burst of nitrogen gas to stir up surface material. The disturbed regolith, a mixture of rocks and dust, was captured in the sampler head. The whole surface contact lasted only about 6 seconds, but the spacecraft collected far more material than expected, so much that some of it was leaking out around the edges of the sampler head before it could be secured. When the sample capsule parachuted to Earth in Utah's desert in September 2023, scientists had high hopes but couldn't be certain what they would find. Remote sensing from orbit can only reveal so much about an asteroid's composition. The actual physical samples, examined in laboratories with the world's most sophisticated analytical instruments, would tell the true story. The material inside exceeded all expectations. The sample mass totaled approximately 122 grams, more than double the mission's minimum requirement of 60 grams. More importantly, the material was extraordinarily rich in scientifically valuable compounds. Initial analyses, published in June 2024 in the journal Meteoritics and Planetary Science by a team led by principal investigator Dante Loretta and sample analysis team leader Harold Connolly, revealed a trove of discoveries. The Bennu samples were dominated by clay minerals, particularly serpentine, a hydrous magnesium silicate that can only form through chemical reactions between rock and liquid water. Serpentine is familiar to geologists on Earth. It's commonly found at mid-ocean ridges, where hot water from hydrothermal vents interacts with the mantle rocks below the oceanic crust. Finding abundant serpentine in the Bennu samples immediately indicated that liquid water had once been present on Bennu's parent body, the larger asteroid from which Bennu is thought to have fragmented long ago. But the serpentine was just the beginning. The sample analysis team found an astonishing diversity of minerals formed through aqueous alteration, the term scientists use for chemical changes caused by interaction with water. There were carbonates, minerals containing carbon and oxygen that precipitate from water solutions. There was magnetite, an iron oxide that can form through water rock reactions. There were sulfides, compounds of sulfur and metals, and phosphates, minerals containing phosphorus that are essential for life as we know it. The presence of all these minerals painted a picture of a parent body that had experienced extensive, complex water rock chemistry over an extended period. Perhaps the most surprising discovery was the presence of magnesium sodium phosphate. This water-soluble mineral hadn't been detected by OSIRIS-REx's remote sensing instruments while the spacecraft was orbiting Bennu. Its presence in the actual samples came as a genuine surprise to the research team. Phosphates are crucial for life. Phosphorus is an essential component of DNA, RNA, ATP, and cell membranes. Finding abundant, pure phosphates in an asteroid sample suggests that the raw materials for life were being synthesized in space long before Earth existed. The phosphate grains in the Bennu sample were notable for their exceptional purity and unusually large size, unprecedented in any meteorite sample previously studied. Similar phosphates had been found in samples from the asteroid Ryugu, returned by Japan's Hayabusa 2 mission, but the Bennu phosphates were different in character, lacking the inclusions of other minerals commonly seen. This purity suggests a unique geochemical environment, possibly involving highly evolved, concentrated brines, similar to those found in evaporating lakes on Earth. What does this mineral assemblage tell us about Bennu's past? According to Loretta, the presence and state of the phosphates, along with the other minerals, suggest a watery history for the asteroid. Bennu, or more accurately its parent body, may have once been part of a small ocean world, an ancient planetesimal with a warm interior sustained by the decay of radioactive elements like aluminium-26 and containing enough water to maintain liquid conditions for extended periods. In this warm, wet interior, water circulated through fractures in the rock, dissolving some minerals and precipitating others, creating the complex assemblage we now find in the Bennu samples. The team also found evidence of fluid flow in the form of veins. Some of the sample particles showed phyllosilicates, the family of minerals that includes clays, filling tiny fractures that cut through the rock. These vein-like structures indicate that water wasn't just present as static pore fluid, but was actively moving through the rock, carrying dissolved substances and depositing new minerals along its path. Images taken by OSIRIS-REx while orbiting Bennu showed similar veins, some up to a meter long, in boulders on the asteroid's surface. Despite this evidence of extensive water interaction, Bennu remains chemically primitive in terms of its elemental composition. When scientists analyzed the bulk chemistry of the samples, they found proportions of elements that closely matched the composition of the Sun's visible surface, the photosphere, for non-volatile elements. This solar-like composition is the hallmark of the most primitive solar system materials, those that have never been significantly processed, melted, or differentiated since the earliest days of the solar system. The carbon and nitrogen content of the Bennu samples was particularly notable. These elements are essential for life, forming the backbone of organic molecules and playing crucial roles in biochemistry. The sample team confirmed that Bennu is remarkably rich in both elements, with organic molecules of stunning complexity and diversity present throughout the material. This wealth of organics, combined with the water-bearing minerals in the phosphates, means that asteroids like Bennu's parent body were carrying essentially a complete prebiotic chemistry kit, all the raw materials needed for the chemical reactions that might eventually lead to life. The D to H ratios measured in the Bennu samples aligned beautifully with Earth's ocean water. This was perhaps the most significant result for understanding the origin of Earth's water. The isotopic match between Bennu's water and Earth's oceans provides direct confirmation that asteroids of this type could have delivered a substantial fraction of our planet's water. It's not just that the minerals look right, the actual isotopic fingerprint of the hydrogen matches what we find on Earth. Meanwhile, Japan's Hayabusa 2 mission had already returned samples from another carbonaceous asteroid, Ryugu, in December 2020. Ryugu is slightly smaller than Bennu, but belongs to the same general class of primitive carbon-rich asteroids. The Japanese mission had collected just over 5 grams of material, less than OSIRIS-REx, but still enough for extensive analysis by teams around the world. Analysis of the Ryugu samples revealed a similar story of aqueous alteration and primitive composition, but with some fascinating differences. Ryugu's samples were remarkably similar to a rare type of meteorite called CI chondrites, named after the Avuna meteorite that fell in Tanzania in 1938. CI chondrites are considered the most primitive known materials in the solar system, with compositions that match the Sun's more closely than any other rock type. Finding that Ryugu essentially matches CI chondrites confirms that these meteorites genuinely represent ancient, unprocessed solar system material, not terrestrial contamination or unusual outliers. But here is where the Ryugu results became truly extraordinary. In 2022, the Hayabusa 2 Initial Analysis Stone Team, a consortium of Japanese universities and research institutions, including the Earth Life Science Institute at Tokyo Tech, announced a remarkable discovery. They had found actual liquid water trapped inside a crystal in one of the Ryugu samples. Not water-bearing minerals, not hydrated compounds. Actual liquid water, encapsulated as a fluid inclusion within a crystal grain. The water was held in micron-sized vasities, too small to see with the naked eye but detectable with advanced analytical techniques, including synchrotron radiation and mass spectrometry. When the team analyzed the composition of this trapped fluid, they discovered it was carbonated water, essentially primordial soda water, containing dissolved carbon dioxide along with salts and organic matter. The implications were staggering. This wasn't just evidence that water had been present in Ryugu's parent body. This was the actual water itself, a pristine sample of the liquid that once flowed through the interior of an ancient asteroid, preserved for more than 4 billion years inside a mineral grain and now brought back to Earth for direct analysis. The crystal that contained this water was pyrrhotite, an iron sulfide mineral, and the fluid inclusions had survived the violent history of the solar system, the collision that destroyed Ryugu's parent body, the vacuum and radiation of space and atmospheric entry, to reach scientists' laboratories intact. Analysis showed that the parent body of Ryugu, formed in the frigid outer regions of the solar nebula, far from the sun, where not only water ice but also carbon dioxide ice could exist as solids. The temperatures in this region must have been approximately -200 degrees Celsius or colder. Based on magnetic records preserved in magnetite crystals within the samples, Ryugu's parent body likely formed in the darkness of the primordial nebular gas cloud, shielded from direct sunlight. After formation, radioactive decay heated the interior, melting the ice and initiating the aqueous alteration that transformed the original rock into the clay-rich material we sample today. The estimated temperature during this aqueous alteration was approximately 25 to 40 degrees Celsius, warm enough for liquid water but cool enough to preserve organic molecules. Within this warm, wet interior, crystals grew from the liquid water. The research team found tabular, coral-like crystal structures that could only have formed by precipitation from a liquid phase. These crystals, growing in the darkness inside an asteroid billions of years ago, record conditions that in some ways resembled early Earth's oceans, a liquid water environment containing dissolved minerals and organic compounds. The D to H ratios in both Ryugu and Bennu samples consistently matched Earth's water. Combined with the mineralogical evidence of aqueous alteration, the discovery of actual preserved liquid water, and the solar-like elemental compositions, these asteroid sample returns have built an overwhelming case. Carbonaceous asteroids, or more specifically their parent bodies from which today's asteroids are fragments, were repositories of ancient water that could have been, and almost certainly was, delivered to Earth through impacts during the early history of our planet. Recent work published in 2025 has added another dimension to this story. Researchers at the University of Tokyo discovered evidence that liquid water may have flowed through Ryugu's parent body, not just during the initial heating phase shortly after formation, but again, much later, perhaps 1 billion years or more after the asteroid originally formed. This late fluid flow may have been triggered by an impact that fractured the rock and melted trapped ice. If carbon-rich asteroids could retain frozen water for over 1 billion years and release it during impacts, they may have been even more effective at delivering water to Earth than previously thought. Calculations suggest that similar bodies colliding with the young Earth might have provided 2 to 3 times more water than earlier models estimated. Understanding that Earth's water came from asteroids and possibly comets is one thing. Understanding exactly when and how it was delivered is another, considerably more complex question. And here, we enter one of the most violent and dramatic chapters in Earth's history. A story of cataclysmic impacts, global melting, and the gradual accumulation of the water that would eventually fill our oceans. When Earth first formed, approximately 4.54 billion years ago, it was a hot, molten ball of rock and metal. This primordial Earth was nothing like the blue marble we know today. The energy of countless collisions, as smaller planetesimals crashed together to build larger bodies, heated the young planet to the point where its entire surface was covered by a vast ocean of magma. Liquid rock hundreds of kilometers deep, glowing red and orange in the darkness of the early solar system. Any water that might have been present in the materials that built Earth would have been devastated by this heat, either vaporized and lost to space, or dissolved into the magma ocean and then degassed into a thick, steam-dominated early atmosphere. During these earliest stages of Earth's formation, conditions were so extreme that maintaining surface water was essentially impossible. The young sun, though actually slightly dimmer than today's sun, was extraordinarily active, bombarding the inner solar system with intense ultraviolet radiation and powerful stellar winds that could strip away atmospheric gases. Any water vapor in Earth's early atmosphere would have been subject to photodissociation, a process where energetic solar radiation breaks water molecules apart into hydrogen and oxygen atoms. The lightweight hydrogen atoms could then escape to space, representing an irreversible loss of water from the system. But Earth didn't finish forming in one smooth, uneventful process. Approximately 50 to 100 million years after the initial assembly of our planet, Earth suffered a catastrophic collision that would reshape it completely. A body roughly the size of Mars, which scientists have named Theia, after the Greek titan who gave birth to the moon goddess Selene, slammed into the young Earth at tremendous velocity. The impact was so violent that it essentially destroyed both worlds, vaporizing vast quantities of rock and creating a combined mass of superheated debris. Both the impactor and a substantial portion of Earth's outer layers were melted and mixed. The combined material formed a structure sometimes described as a synestia, a donut-shaped cloud of vaporized rock extending tens of thousands of kilometers into space. Over the following centuries and millennia, this debris gradually cooled and coalesced. Most of it fell back onto Earth, but a fraction remained in orbit and eventually aggregated to form our moon. The moon-forming impact represents a dramatic reset in Earth's volatile history. Whatever water Earth might have accumulated during its initial formation, whatever was dissolved in its magma ocean or present in its early atmosphere, was likely lost in this cataclysm. The energy of the Theia impact was sufficient to vaporize rock and metals. Water didn't stand a chance. Earth essentially had to start over, cooling from yet another magma ocean phase, this time with a newly formed moon-keeping gravitational company. As the magma ocean cooled and solidified over the following millions of years, Earth's surface became progressively more stable. A thin crust of rock formed on top of the magma, like ice freezing on a pond. This early crust was probably basaltic in composition, similar to the rock that makes up Earth's ocean floors today, dark and dense with relatively low silica content. Beneath this thin lid, magma continued to churn and convect, driven by the tremendous heat stored in Earth's interior. But where would the water come from to fill Earth's oceans? The planet had been essentially sterilized of its volatile inventory by the heat of formation and the moon-forming impact. Any subsequent water would have to be delivered from elsewhere. Enter what scientists call the late veneer. In the first few 100 million years after the moon formed, Earth continued to be bombarded by asteroids and comets. This wasn't unusual. The entire inner solar system was being cleaned out during this period as the newly formed planets gravitationally perturbed the orbits of leftover planetesimals. Rocky debris that had failed to be incorporated into planets during the main accretion phase was now being swept up through countless collisions. Many of these impacting bodies, especially those from the outer asteroid belt and beyond, would have been rich in water. The term late veneer refers specifically to the material accreted by Earth after the core had finished forming and the moon-forming impact had occurred. This material is called a veneer because it represents a relatively thin layer added on top of Earth's already assembled bulk. Current models suggest that the late veneer may have contributed approximately 1% of Earth's total mass, maybe less. In absolute terms, though, this is still a staggering amount of material, equivalent to perhaps a billion tons of asteroids and comets, tens of thousands of objects larger than a kilometer across, plus countless smaller fragments. 1% of Earth's mass might not sound like much, but it's more than enough to account for all the water in Earth's oceans, mantle, and atmosphere. If just 10% of the late veneer material was water, whether as ice or as water-bound in minerals, that would still represent many times the mass of all Earth's surface water. The late veneer could easily have delivered our entire oceanic inventory with room to spare. The timing of water delivery matters enormously for understanding when conditions on Earth became suitable for life. If Earth remained dry for hundreds of millions of years after the moon-forming impact, life would have had to wait. But if water arrived relatively quickly, within the first 100 million years or so, then conditions could have been right for life to begin remarkably early in Earth's history. Here is where some of the most remarkable evidence comes into play. The oldest known materials that formed on Earth, zircon crystals from the Jack Hills region of Western Australia, date to approximately 4.4 billion years ago. Zircons are extraordinarily tough minerals, composed of zirconium silicate, that can survive conditions that would destroy almost any other rock. They form when granitic magmas cool, crystallizing out as tiny, typically microscopic grains that can then be preserved for billions of years, even as the rocks containing them are eroded, transported, buried, and metamorphosed. In 2001, a team led by Simon Wild at Curtin University in Australia, working with John Valley at the University of Wisconsin-Madison, published a groundbreaking study of Jack Hills zircons. They found zircon crystals dating to 4.4 billion years ago, just 160 million years after the moon-forming impact. But even more remarkable was what the chemical composition of these zircons revealed. When scientists analyze the oxygen isotopes in zircon crystals, they can infer something about the conditions under which the magmas that formed those crystals originated. There are 3 stable isotopes of oxygen: oxygen-16, oxygen-17, and oxygen-18. The ratios of these isotopes vary depending on temperature, the presence of water, and the history of the materials involved. Magmas that form from rock that has interacted with surface water have a distinctive oxygen isotope signature, different from magmas derived directly from the mantle. The Jack Hills zircons showed oxygen isotope ratios consistent with formation from magmas derived from rocks that had been altered by surface water. In other words, the parent rocks of those 4.4 billion-year-old zircons had been in contact with liquid water on Earth's surface. If this interpretation is correct, and subsequent work by Valley's group using advanced atom probe tomography techniques has confirmed the age determinations, then Earth had liquid water on its surface within approximately 100 million years of the moon-forming impact. That's remarkably fast by geological standards. Valley and his colleagues announced in 2014 that atom probe tomography analysis had definitively confirmed that the oldest Jack Hills zircons were indeed 4.375 billion years old, plus or minus 6 million years. The technique allowed them to count individual lead atoms within the crystal structure, resolving concerns that previous dating methods might have been affected by lead mobility within the crystals. The confirmation strengthened the case for a cool early Earth, a concept that stands in stark contrast to the traditional picture of the Hadean Aeon as an unremittingly hellish period. The emerging picture is of an Earth that cooled surprisingly quickly after the moon-forming impact. Within perhaps 100 million years, temperatures had dropped enough for a solid crust to form, for an atmosphere to stabilize, and for liquid water to condense on the surface. This water must have come from the late veneer, delivered by the ongoing bombardment of water-rich asteroids and perhaps comets. The delivery was rapid enough that oceans may have existed within a few tens of millions of years after the crust solidified. But was this period of bombardment continuous and gradual? Or did it vary in intensity over time? This question brings us to one of the most debated topics in planetary science, the late heavy bombardment. When Apollo astronauts brought back samples of lunar rock in the late 1960s and early 1970s, scientists analyzed them to determine when the impacts that created the moon's Great Basins had occurred. The results were intriguing. Impact melt rocks from multiple sites showed evidence of major collisions clustered around 3.9 billion years ago, roughly 600 million years after the moon formed. This suggested that rather than a smooth decline in bombardment over time, there had been a spike in impacts around this period. The idea of a late heavy bombardment, sometimes called the lunar cataclysm, gained further support from theoretical models. The NICE model, named after the French city where it was developed, proposed that about 4 billion years ago, the giant planets underwent a period of orbital instability. Jupiter, Saturn, Uranus, and Neptune may have migrated significantly from their original positions, and this reorganization would have gravitationally scattered huge numbers of asteroids and comets into the inner solar system. The resulting bombardment could have been devastating, with large impacts capable of vaporizing oceans and sterilizing the surface. However, more recent research has cast doubt on whether the late heavy bombardment was as intense or as sudden as once thought. Work by Stephen Mazes at the University of Colorado Boulder and colleagues, published in 2019, examined ages from 60,000 meteorites and found no evidence for a spike in impact rates at 3.9 billion years ago. Instead, they found that the most intense period of bombardment ended much earlier, around 4.48 billion years ago, just 80 million years after the solar system began to form. Moises argues that the apparent clustering of lunar impact ages around 3.9 billion years may be a sampling artifact. All of the Apollo landing sites were located in a relatively small region of the moon's near side, and they may have been disproportionately influenced by debris from a single large basin-forming impact, the Imbrium impact, which occurred around that time. If true, the bombardment may have declined more steadily than previously believed, without a dramatic late spike. This alternative timeline has important implications for life on Earth. If heavy bombardment ended by 4.48 billion years ago, rather than 3.9 billion years ago, Earth's surface may have become habitable much earlier than the traditional late heavy bombardment scenario allows. There would have been more time for the chemistry of life to begin, for the first organisms to emerge and diversify before conditions became harsh enough to be recorded in the rock record that survives today. Whatever the precise timeline, one thing is clear. By 4 billion years ago at the latest, and possibly much earlier, Earth had liquid water oceans. The atmosphere was thick, probably dominated by carbon dioxide and nitrogen with traces of other gases, but essentially no free oxygen. The surface was still geologically active, with volcanic eruptions and hydrothermal systems common. And somewhere in those warm oceans, or in hydrothermal vents on the seafloor, or in pools on volcanic islands, the chemistry that would lead to life was beginning. We don't know exactly when life started. The oldest definitive fossils, stromatolites formed by photosynthetic microorganisms, date to approximately 3.5 billion years ago. But there are hints of possible life signatures in much older rocks. Carbon isotope ratios in some ancient sediments suggest biological processing as far back as 3.8 billion years. And in 2015, researchers reported finding graphite inclusions with potentially biological carbon isotope signatures in 4.1 billion-year-old zircons from Jack Hills, though this claim remains controversial. If life did emerge that early, it would have needed water. And thanks to the late veneer, that water was already present, delivered by the same asteroids and comets that had inherited it from ancient molecular clouds and carried it through the violence of solar system formation to the surface of our young planet. Let's step back for a moment and consider what all this means at the molecular level. When we say that water is older than the sun, we're not saying that every individual water molecule in your glass has remained intact for 4.6 billion years. Water molecules are dynamic. They break apart and reform constantly. In liquid water, hydrogen bonds between molecules form and break trillions of times per second. Water participates in countless chemical reactions, dissolving minerals, breaking down organic compounds, and serving as a medium for the chemistry of life. Individual water molecules have lifetimes measured in fractions of a second before they exchange atoms with their neighbors. What we mean, rather, is that the atoms themselves, the hydrogen and oxygen that compose water, have been cycling between different chemical forms since before the sun existed. Some fraction of those atoms was bound together as water molecules in the molecular cloud that gave birth to our solar system. They stuck to dust grains, coating them with ice in the frigid darkness of interstellar space. When the cloud began to collapse and the solar system began to form, many of those ice-coated grains were incorporated into larger bodies, the asteroids and comets that would later deliver water to Earth. Some of that original molecular cloud ice survived intact through the violent process of stellar birth, protected by the insulating layers of dust and rock around it. The isotopic composition of water molecules serves as a chemical fingerprint that records their formation conditions and history. Ordinary water, H2O, consists of two atoms of the most common hydrogen isotope, hydrogen-1 or protium, bonded to one oxygen atom. But a small fraction of water molecules contain deuterium, hydrogen-2, the heavier isotope with one proton and one neutron in its nucleus. Water containing one deuterium atom is called HDO, sometimes called semi-heavy water, and it's about 1 part in 6,400 compared to ordinary H2O in Earth's oceans. The ratio of deuterium to hydrogen in water is not random. It reflects the conditions under which the water formed and the processes it has undergone since. In the cold environments of molecular clouds, where temperatures hover near absolute zero, deuterium chemistry is enhanced. This happens because of subtle quantum mechanical effects that become important at very low temperatures. When hydrogen atoms react on the surfaces of dust grains, deuterium atoms react slightly more readily than ordinary hydrogen, because the heavier isotope sits a bit lower in energy wells. The result is that ice formed in molecular cloud conditions tends to be enriched in deuterium compared to the overall deuterium to hydrogen ratio in the universe. This deuterium enrichment is a signature of cold formation, water that forms at higher temperatures in warmer environments closer to stars. Tends to have lower D to H ratios. By measuring the D to H ratio in different solar system objects, scientists can infer something about where and under what conditions their water formed. Comets from the distant Oort cloud, which formed in the coldest regions of the solar system, tend to have the highest D to H ratios. Asteroids that formed closer to the Sun generally have lower ratios. Earth's water falls somewhere in between, suggesting contributions from multiple sources that formed under a range of conditions. One of the most significant advances in understanding the origins of solar system water came from observations of a young stellar system called V8883 Orionis, located approximately 1,305 light-years from Earth in the constellation Orion. V8883 Orionis is a protostar, a star still in the process of forming, surrounded by a protoplanetary disk of gas and dust from which planets may eventually emerge. Unlike most protostars, V8883 Orionis is currently experiencing an outburst, a period of increased brightness caused by enhanced accretion of material onto the central star. This outburst has heated the surrounding disk, pushing the water snow line, the boundary where water transitions from ice to vapor, out to a distance of about 80 astronomical units from the star, roughly twice the size of Pluto's orbit. This expanded snowline gave astronomers an unprecedented opportunity. Normally, the snowline in protoplanetary disks is too close to the central star to be observed directly. The warm water vapor near the star is blocked by the dusty disk, and the ice further out cannot be easily detected. But V8883 Orionis' outburst moved the snowline far enough out that the Atacama Large Millimeter Submillimeter Array, ALMA, could detect gaseous water in the disk and measure its composition. In March 2023, a team led by John Tobin of the National Radio Astronomy Observatory published groundbreaking results from ALMA observations of V8883 Orionis. They detected both ordinary water and HDO, heavy water containing deuterium, in the protoplanetary disk. By measuring the ratio of these two forms of water, they could determine the D to H ratio of the disk water and compare it to water in our own solar system. The results were stunning. The D to H ratio in V8883 Orionis matched that in solar system comets and in protostars still embedded in molecular clouds. The water in this young planetary system, still in the process of forming, already had the same isotopic composition as water that would eventually be incorporated into comets and delivered to planets. This meant that water wasn't being significantly processed or altered during the disk phase. It was being inherited essentially unchanged from the molecular cloud. As Tobin explained, scientists had previously been able to link Earth's water to comets and to link water in protostars to water in the interstellar medium, but they couldn't connect protostars to comets. V883 Orionis provided that missing link. The observations demonstrated an unbroken chain in the lineage of water, from molecular clouds to protostars to protoplanetary disks to comets to planets. The water we drink today carries the chemical signature of its formation in a cold molecular cloud, billions of years before our sun began to shine. In October 2025, the same research group published even more remarkable findings. Using ALMA's sensitive Band 7 receivers, they detected D2O, doubly deuterated water where both hydrogen atoms are replaced by deuterium in the V883 Orionis disk. D2O is sometimes called heavy water in the strictest sense, though HDO also goes by that name colloquially. The detection of D2O was particularly significant because it forms almost exclusively under the coldest conditions, where even normal deuterium enrichment processes are amplified. Finding D2O in the disk provided unequivocal proof that the water observed was ancient, predating the star itself and preserving a chemical record of interstellar cloud conditions. This work, led by Margot Limker of the University of Milan, showed that some of the water found in forming planetary systems must be older than the central stars around which those systems are developing. The water in V883 Orionis's disk formed at the earliest stages of star and planet formation, probably in the molecular cloud before the cloud even began to collapse. It has survived the chaotic processes of stellar birth, traveling billions of kilometers through space and time, and it will eventually be incorporated into whatever planets, comets, and asteroids form in that system. The implications extend far beyond our own solar system. If water is routinely inherited from molecular clouds into forming planetary systems without being reset or significantly processed, then every planetary system should start with a substantial inventory of water carrying the isotopic signature of its interstellar origins. This is encouraging news for astrobiology. It suggests that water, the essential solvent for life as we know it, is essentially a default ingredient in planet formation, delivered automatically as part of the standard package of materials that goes into building a solar system. The chemistry of ancient water involves more than just hydrogen and oxygen isotopes. Water in molecular clouds and protoplanetary disks is never pure. It exists as part of a complex mixture of ices coating dust grains. When scientists analyze the composition of comets and carbonaceous meteorites, they find not just water ice, but a rich cocktail of other frozen compounds: carbon dioxide, carbon monoxide, methane, ammonia, formaldehyde, methanol, and dozens of more complex organic molecules. These ices form through surface chemistry on dust grains in molecular clouds. Hydrogen atoms landing on grain surfaces can react with other atoms and molecules to form new compounds. Oxygen atoms become hydroxyl radicals, then water. Carbon atoms combine with hydrogen and oxygen to form various organic molecules. Nitrogen participates in reactions that produce ammonia and nitrogen-bearing organics. The grain surfaces act as catalysts and templates, enabling reactions that would be impossibly slow in the gas phase. As grains accumulate thicker ice mantles, the chemistry becomes more complex. Ultraviolet radiation from nearby stars, cosmic rays, and radioactive decay within the grains themselves provide energy to drive further reactions. Laboratory simulations have shown that irradiating ice mixtures similar to those found in molecular clouds can produce an astonishing variety of organic compounds, including amino acids, the building blocks of proteins, and nucleobases, the information-carrying components of DNA and RNA. When this ice is delivered to planets through asteroid and comet impacts, it brings along not just water, but this entire chemical inventory. The organic molecules found in carbonaceous chondrite meteorites and now in samples from asteroids Bennu and Ryugu include amino acids of both biological and non-biological types. The Murchison meteorite, a carbonaceous chondrite that fell in Australia in 1969, contains over 90 different amino acids, far more than the 20 used by life on Earth. Analysis of Ryugu samples identified more than 20,000 distinct molecular compositions containing carbon, hydrogen, nitrogen, oxygen, and sulfur. The Bennu samples contained 14 of the 20 protein-forming amino acids used by life, plus a tentative detection of tryptophan, the 15th, which had never before been confirmed in extraterrestrial material. Many of these organic molecules show the same deuterium enrichment that the water does, confirming that they formed under similar cold conditions in the molecular cloud or the outer regions of the protoplanetary disk. Some molecules show enrichments in other isotopes as well, including carbon-13 and nitrogen-15, additional signatures of low-temperature chemistry in the pre-solar environment. Perhaps most intriguingly, some of the amino acids in meteorites show what's called enantiomeric excess, a slight preference for one mirror image form over the other. Amino acids can exist in two forms, called L and D enantiomers, that are mirror images of each other, like left and right hands. Life on Earth uses almost exclusively L amino acids in proteins. If meteoritic amino acids showed random mixtures of L and D forms, it would suggest that the preference for L amino acids arose on Earth after life began. But some carbonaceous chondrites show small but measurable excesses of L amino acids, suggesting that the chirality, the handedness of biological molecules may have extraterrestrial origins. The water delivered to Earth was never pure H2O. It was always part of a complex chemical mixture, a treasure trove of molecular building blocks that made our planet not just wet, but chemically rich, prepared with the raw materials from which life could potentially emerge. The same deuterium-enriched water that records its formation in a cold molecular cloud also came packaged with the organic molecules that, under the right conditions, could begin the long climb toward biological complexity. When you drink a glass of water, you're consuming molecules whose atoms have cycled through this cosmic journey. The hydrogen in that water may have been part of a molecule that stuck to a dust grain in a dark molecular cloud billions of years before Earth existed. The oxygen may have been forged in the nuclear furnace of a massive star that died in a supernova explosion, scattering its processed material into space to seed future generations of stars and planets. Those atoms found each other in the cold darkness between the stars, stuck to a grain of silicate dust, and remained frozen together through the collapse of a molecular cloud, the birth of the sun, the formation of asteroids, billions of years of cold storage, a violent impact with the young Earth, 4 billion years of cycling through oceans and atmosphere and rock and living things, until finally, improbably, impossibly, they reached your glass. The chemistry of ancient water connects us directly to the cosmos. We are not separate from the universe, we are made of it. The water that makes up 60% of your body carries isotopic signatures of its formation in environments so cold and dark that even the chemistry of life would be impossible there. Yet, that water and the organic molecules that came with it provided the foundation for everything that followed: the first cells, the evolution of complexity, the emergence of consciousness, and your ability to contemplate the remarkable journey that brought that water to you. Earth is not the only water world in our solar system, not even close. When we look at the distribution of water across our cosmic neighborhood, we find it in surprising places and in quantities that dwarf Earth's oceans. Jupiter's moon Europa, for instance, is thought to harbor an ocean of liquid water beneath its icy crust that contains more water than all of Earth's oceans combined. Saturn's moon Enceladus has a similar subsurface ocean, which we know is connected to the surface because we've observed geysers erupting through cracks in the ice, spewing water vapor and ice particles into space. The Cassini spacecraft flew through these plumes and tasted their composition. The water contains salts, organic molecules, and even silica particles, suggesting active hydrothermal vents on the ocean floor beneath tens of kilometers of ice. Jupiter's moon Ganymede, Saturn's moon Titan, and several other outer solar system moons are also thought to have subsurface oceans. Even Pluto might have one, kept liquid by the decay of radioactive elements in its interior and the insulating properties of its thick ice shell. All of this water, in the ocean moons, in the comets of the Kuiper Belt and Oort cloud, in the icy mantles of outer asteroids, shares a common origin. It formed in the cold outer regions of the protoplanetary disk, where temperatures remained below the freezing point of water throughout the sun's formation. It contains the deuterium-enriched signature of ancient molecular cloud water, inherited from before the solar system began. Closer to the sun, water becomes scarcer, but no less interesting. Mars once had abundant liquid water on its surface. We can see the evidence in dried-up river valleys, ancient lake beds, and layered sedimentary rocks that could only have formed in the presence of water. Much of that water is now locked up as ice at the poles or as permafrost beneath the surface, but some has been lost to space, stripped away by the solar wind after Mars lost its protective magnetic field. Venus might once have had oceans too, though if it did, they boiled away as the planet's atmosphere grew thick and hot due to a runaway greenhouse effect. Today, Venus's atmosphere contains only traces of water vapor, and the deuterium to hydrogen ratio is extremely high, about 150 times higher than Earth's. This tells us that Venus has lost most of its hydrogen to space, preferentially losing the lighter isotope and leaving the heavier deuterium behind. Even Mercury, the closest planet to the Sun, has water ice in permanently shadowed craters at its poles, where temperatures never rise above about -170 degrees Celsius, despite the planet's proximity to the Sun. The Moon, too, has water, though in much smaller quantities than we once thought. It exists as ice in permanently shadowed polar craters and as hydroxyl groups bound to minerals across much of the lunar surface, created by the interaction of solar wind hydrogen with oxygen in the rocks. All of this water has the same ultimate origin, the molecular clouds of the interstellar medium. The details of how it was delivered to each body vary. The chemistry of how it has been processed and altered varies. But the fundamental source, ancient water from before the sun, remains the same throughout the solar system. One of the most profound implications of discovering that Earth's water is older than the sun is what it tells us about the potential for life elsewhere in the universe. If water formation in molecular clouds is a common process, and all the evidence suggests it is, then every newly forming planetary system should inherit a substantial inventory of water from its parent cloud. The V883 Orionis observations confirmed this. The water in that young stellar system has the same ancient signature as water in our solar system, and presumably every other planetary system formed from molecular clouds will be similarly endowed. This is enormously encouraging for astrobiology. It means that the basic ingredient for life as we know it, liquid water, should be available around essentially every star. The question isn't whether water exists, but whether conditions allow it to remain in liquid form on a planet's surface or to exist as a subsurface ocean in moons or dwarf planets. The habitable zone, the region around a star where temperatures allow liquid water on a planet's surface, depends on the star's luminosity and the planet's atmosphere. For a star like our Sun, it extends roughly from about 0.9 to 1.5 astronomical units. Earth sits right in the middle of that zone, which is why we have stable liquid water oceans. But we now know that habitable conditions can exist far beyond the traditional habitable zone. Europa and Enceladus orbit well outside the Sun's habitable zone, yet they have liquid water oceans kept warm by tidal heating. Gravitational interactions with their parent planets flex their interiors, generating heat through friction. These ocean worlds might be habitable, at least in principle, even though they receive only a tiny fraction of the sunlight that Earth does. If ocean worlds like Europa and Enceladus exist in our solar system, they likely exist around other stars too. And that vastly increases the number of potentially habitable environments in the galaxy. Moreover, the fact that water is inherited from molecular clouds means that it brings along a rich chemical inventory. The same processes that form water in molecular clouds also form organic molecules. So every planetary system starts out with not just water, but with complex carbon chemistry, with the raw materials for prebiotic evolution. This doesn't guarantee that life will emerge. We don't know how difficult the origin of life is. It might be common, happening wherever conditions are suitable. It might be rare, requiring a particular combination of circumstances that occurs only occasionally. But at least we can say with confidence that the basic ingredients, water and organic molecules, are widespread, possibly universal, in planetary systems. When we look up at the night sky and see the Orion Nebula, that vast stellar nursery where thousands of stars are being born, we can know that water is forming there right now. Ice is coating dust grains in the cold, dark regions of that nebula. Someday, millions of years from now, that ice will be incorporated into new planetary systems. It will become oceans on alien worlds, subsurface seas on distant moons, and on some of those worlds, in those seas, chemistry might cross the threshold to biology. Our water's ancient origin connects us to that process, to the vast cycle of stellar birth and death, cloud formation and collapse, chemistry and perhaps biology, playing out across the galaxy. Despite all that we've learned, significant mysteries remain about Earth's water and its origins. One major question is the relative contribution of different sources. How much water came from asteroids? How much from comets? Did most arrive during Earth's accretion and the late Veneer period, or was there significant delivery later during the late heavy bombardment? The D to H ratios give us clues, but they don't provide a complete answer, because different populations of asteroids and comets have different ratios. There's also the question of indigenous hydrogen. Some models suggest that Earth might have incorporated significant amounts of hydrogen during its formation, possibly from the solar nebula gas that was still present when Earth was forming. This hydrogen could have reacted with oxygen in Earth's mantle to form water internally. If this happened, it would add another component to Earth's water budget, one with a different isotopic signature than the water delivered by asteroids and comets. The Rosetta reanalysis showing that Comet 67P's nucleus water has a D to H ratio similar to Earth's is a major development, but it's based on one comet. We need measurements from more comets, ideally from direct samples, to understand the full diversity of cometary water and its potential contribution to Earth's oceans. Similarly, while the Bennu and Ryugu samples have provided unprecedented information about carbonaceous asteroids, they represent only two objects from a diverse population. Different carbonaceous asteroids might have different water contents and different isotopic signatures, reflecting their formation in different locations or at different times in the early solar system. There are also mysteries about the process of water delivery itself. How efficiently did asteroids and comets deliver their water to Earth? When they impact a planet, much of the water might be vaporized and lost to space, especially during high-velocity impacts. The conditions that allow water to be retained, impact velocity, angle, the presence of an atmosphere, the target material, are complex and not fully understood. Future missions will help address these questions. The European Space Agency's Comet Interceptor mission, scheduled to launch in the late 20s, will visit a pristine comet from the Oort cloud, one that has never entered the inner solar system before. This will provide our first close-up look at a truly pristine cometary body, and might reveal whether Oort cloud comets are as different from Earth's water as the earlier measurements suggested, or whether those measurements were affected by surface processing that occurs when comets repeatedly approach the Sun. NASA's Dragonfly mission, scheduled to launch in 2027, will explore Saturn's moon Titan, which has a thick atmosphere and lakes of liquid methane on its surface, but also a subsurface water ocean. Studying Titan will help us understand how water behaves and evolves in environments very different from Earth. Sample return missions to Mars might bring back rocks that contain water, either as ice or bound in minerals, allowing us to compare Martian water with Earth's and with carbonaceous asteroids. If Mars samples show a similar deuterium signature to Earth's water, it would confirm that both planets were hydrated by the same population of water-rich asteroids in the early solar system. Ground-based and space-based telescopes continue to observe water in protoplanetary disks around other stars. The James Webb Space Telescope, with its powerful infrared instruments, can detect water vapor in these disks and measure its deuterium content, extending the observations begun with ALMA and refining our understanding of how universal the process of ancient water inheritance really is. Each of these missions and observations will add pieces to the puzzle, helping us understand not just where Earth's water came from, but how common water-rich planets might be, how water shapes planetary evolution, and what role it plays in the emergence and sustenance of life. Let's return, finally, to that glass of water in your hand. We've traced its history across 13.8 billion years, from the first hydrogen nuclei formed in the Big Bang, through the forges of ancient stars that created oxygen, into the cold dark of molecular clouds where water first condensed on dust grains, surviving the violent birth of our sun, being incorporated into asteroids and comets, delivered to a young Earth through countless impacts, cycling through oceans and rocks and atmospheres for 4.5 billion years, passing through rivers and glaciers and living organisms, evaporating and raining down again and again in the endless hydrologic cycle, until finally, improbably, impossibly, it arrives in your glass. Every water molecule in your body has been on this journey. The water in your cells, in your blood, in your neurons, all of it is ancient beyond comprehension. When you drink, you're drinking starlight, drinking the remnants of molecular clouds, drinking the heritage of the universe itself. This isn't just a matter of scientific interest, though the science is fascinating. It's a statement about our connection to the cosmos. We are not separate from the universe. We are made of it. The water that makes up 60% of your body is the same water that formed before the sun existed. You are, quite literally, made of stardust and ancient water. This realization should fill us with wonder. In our everyday lives, water is so common, so ordinary, that we take it for granted. We use it to wash dishes, water plants, and fill swimming pools. But every drop has a cosmic heritage, a history that spans the lifetime of the universe. It should also fill us with humility. Earth's water wasn't made for us. It doesn't exist because we need it. It predates our planet by hundreds of millions of years. It predates our sun. It formed through natural processes in the interstellar medium, was incorporated into the solar system by chance, delivered to Earth by the random chaos of planetary formation, and only then, only after all of that, became the medium in which life, our life, could emerge and evolve. We are the beneficiaries of a cosmic inheritance, recipients of water that has traveled across space and time to make our existence possible. Without that ancient water, there would be no oceans, no rain, no rivers, no life. Earth would be as dry and dead as the moon, a barren rock orbiting a star in an unremarkable corner of the galaxy. But because water from ancient molecular clouds found its way here, because carbonaceous asteroids and perhaps comets delivered their precious cargo during the first few 100 million years of Earth's history, we have this beautiful, improbable, living world. The story of Earth's water doesn't end with the present. Water continues to cycle through our planet's systems, and it will continue to do so for billions of years to come, though the details will change as the sun evolves and Earth ages. Right now, at this moment, water is evaporating from the oceans, rising into the atmosphere, condensing into clouds, falling as rain or snow. It's flowing through rivers to the sea, percolating through soil and rock. emerging in springs, cycling through the bodies of countless organisms. Every year, the entire ocean evaporates and falls again, not all at once, but molecule by molecule, in a constant exchange between ocean, atmosphere, land, and life. Some water gets temporarily locked away in more permanent reservoirs. When organisms with shells or skeletons die, they carry water molecules to the ocean floor, where they're incorporated into sediments. Those sediments get buried, compressed, and eventually subducted into the mantle as tectonic plates converge. The water descends deep into Earth's interior, where it might remain for hundreds of millions of years before being returned to the surface through volcanic eruptions. There's actually more water stored in Earth's mantle than in all the oceans combined, perhaps 10 to 20 times as much, bound up in minerals deep beneath our feet. This mantle water moves on geological timescales, cycling between the interior and the surface through the slow churning of plate tectonics. On even longer timescales, Earth is slowly losing water to space. High in the atmosphere, ultraviolet light from the sun breaks water molecules apart into hydrogen and oxygen. The hydrogen, being light, can escape Earth's gravity and drift away into space, lost forever. This process is extremely slow. Earth loses only a tiny fraction of its water this way over millions of years. But it's not zero. Over billions of years, it adds up. The sun is gradually getting brighter as it ages, increasing in luminosity by about 1% every 100 million years. In a billion years or so, the sun will be hot enough that Earth's oceans will begin to evaporate more rapidly. Eventually, Earth will suffer the same runaway greenhouse effect that turned Venus into a hellish hothouse. The oceans will boil away completely, and Earth will lose most of its water to space, just as Venus did. But that's a billion years in the future. For now, and for the foreseeable future of our species and our descendants, Earth will remain a water world, blue and beautiful, the only place in the solar system where liquid water rests on the surface of a planet, where that water supports a global biosphere of stunning complexity and diversity. And all of it, every ocean, every raindrop, every ice crystal, every cell in every living thing, owes its existence to water that formed before the sun, in the cold darkness between stars. Understanding that Earth's water is older than the sun fundamentally changes how we think about our place in the universe. For most of human history, we saw ourselves as central, special, the point and purpose of creation. The Earth was the center of the universe, the sun and stars wheeled around us, and everything existed for our benefit. Then Copernicus and Galileo showed us that Earth orbits the sun, not the other way around. We were displaced from the center. Then we learned that the sun is just one star among hundreds of billions in our galaxy, and our galaxy is just one among hundreds of billions of galaxies. We were displaced again, becoming increasingly peripheral, increasingly ordinary in the grand scheme of things. But now, in a curious reversal, we discover that we're connected to that grand scheme more intimately than we imagined. The water in our bodies, the substance that makes up most of our cells, is older than our home star. It links us directly to the most ancient and widespread processes in the universe: the formation of stars, the chemistry of molecular clouds, the inheritance of matter from generation to generation, of stellar birth and death. We are not separate from the cosmos. We are not observers looking at the universe from outside. We are part of it, made of it, shaped by it. The atoms in our bodies were forged in stars. The water we drink formed in interstellar clouds. The energy that powers our civilization comes from ancient sunlight, captured by plants and buried as fossil fuels over millions of years, or captured by solar panels and used immediately. Every aspect of our existence is woven into the fabric of the universe. We are not tourists here. We are natives, born of stardust and ancient water, shaped by 4 billion years of evolution on a planet that itself formed from the debris of earlier stars. This perspective, sometimes called the cosmic perspective, should inform how we think about ourselves and our future. It should make us appreciate the rarity and preciousness of life, aware that while the ingredients for life might be common, life itself is precious precisely because it is complex, fragile, and not inevitable. It should make us protective of Earth, understanding that this is the only world we know for certain that hosts life, the only world in our neighborhood where ancient water became seas, where seas became the cradle for biology, where biology became us. And it should fill us with a sense of connection to the universe at large, knowing that the same processes that created us are creating new stars and planets right now in stellar nurseries across the galaxy, and that some of those planets will surely be showered with ancient water just as Earth was, and perhaps on some of them, that water will nurture life. We are one chapter in a story that began with the Big Bang and will continue for trillions of years into the future. We're a small chapter, a brief one, but we're part of the story nonetheless. Understanding our water's ancient origin helps us see that it helps us place ourselves in the flow of cosmic time. So the next time you take a sip of water, pause for a moment. Think about the journey those molecules have taken. They formed in a molecular cloud before the sun existed. They coated dust grains with ice in conditions of cold and dark that we can barely imagine. They survived the violent birth of a star, were incorporated into asteroids or comets, traveled through the early solar system, collided with a young Earth, cycled through oceans and atmosphere and rock for billions of years, passed through countless living organisms, evaporated and rained down again and again, and finally arrived, against all odds, in your glass. You hold in your hand a bit of the ancient universe, a sample of matter older than the sun, a liquid that links you to the most fundamental processes of chemistry and physics playing out across space and time. It's just water. Simple, ordinary, everyday water. But it's also a miracle, a wonder, a connection to everything that has ever been and everything that will ever be. The water you drink is older than the sun. Remember that. Hold it in your mind like you hold that glass in your hand. Let it change how you see the world, how you see yourself, how you see your place in this vast, ancient, magnificent universe we call home. If you found this journey through deep time as fascinating as I hoped you would, please consider liking this video and subscribing to Deep Calm Science. There are more stories to tell, more wonders to explore, more connections to draw between the everyday and the cosmic. And all of it is waiting for us, written in the rocks, the stars, and yes, even in the water we drink every day. Until next time, stay curious, stay humble, and remember, you're made of ancient water and starlight.